All right, let's jump right in. Today we're tackling something that is, and I mean this, absolutely foundational for anyone who works with data. Figuring out if your data is normal. Now, it sounds kind of basic, right? But trust me, getting this one step right is often the difference between a real breakthrough and a conclusion that's just flat out wrong.
So, let me just start by asking you this. Is your data lying to you? Seriously, because it just might be. If we just assume our data is well behaved without actually checking, we can be led down a completely wrong path. The story we think we're seeing might not be the real story at all.
Okay, so what do we even mean by normal data? Well, it's all about how closely your data fits that classic, perfect, symmetrical bell curve. You know the one. The thing is, a huge number of our most powerful statistical tools are built on the assumption that your data looks just like this. If your data doesn't fit this pattern, well, those tools don't just bend, they break.
So here's our game plan. Think of it like we're building the ultimate data analyst's toolbox. First, we'll cover why this is so critical. Then, we'll look at the classic tools everyone knows. But then, and this is where it gets fun, we'll talk about when those classic tools just don't cut it and what advanced methods we can pull out instead. And finally, we'll tie it all together so you know exactly how to pick the right tool for the job.
Okay, first up, let's talk about why this matters so much, and the hidden and sometimes pretty serious risks of getting this wrong.
Look, the stakes here are huge. This isn't just some boring academic exercise. If you get the normality assumption wrong, you could be looking at biased results, error rates that are totally off the charts, and conclusions that just aren't reliable. Imagine a clinical trial where the results are just wrong. That's what we're talking about. This isn't just about the math, it's about the entire integrity of your work.
All right, let's open up that toolbox and look at the classics, the first tools that pretty much everyone reaches for.
Before you even think about crunching a single number, you got to do one thing first. Just look at your data. And the best way to do that is with something called a QQ plot. Think of it as a simple but powerful eye test for your data set. It lets you visually check if your data points are lining up nicely with where they should be in a perfect normal distribution. Honestly, your eyes can catch problems that a purely numerical test might miss entirely.
So, after the eye test, you might bring out the big guns. The two heavy hitters you see here are Shapiro-Wilk, which is great for smaller datasets, and Jarks-Bara, which looks at how lopsided your data is and how peaky it is. They're both powerful, for sure, but here's their Achilles heel, and it's a big one. They are both incredibly sensitive to outliers, those few extreme data points that can throw the whole analysis off.
And this is where things get really interesting. Because in the real world, data is messy. It doesn't always play by the rules. And those classic tools we just talked about, well, they can break.
So what are these data gremlins that cause all the trouble? Well, you've got outliers, of course. You have tiny sample sizes where you just don't have enough information to be confident. You have heavy tails, which is just a fancy way of saying your data has more extreme values than you'd expect. And then you have complex signals, data that's just all over the place, totally unpredictable. This is where those classic tests really start to struggle.
So what do you do when the standard tools aren't enough? Well, you don't give up. You reach for the specialist's toolkit. These are the advanced methods designed for exactly these kinds of tough jobs.
Okay, so problem number one, outliers and those heavy tails. The solution is something called an L-moment test. See, classical tests often square values, which makes extreme data points have a huge effect. But L-moment tests are smarter. They use linear combinations, which basically means they don't overreact to a few weird points. They're like a heavy-duty wrench that won't slip, even on the toughest bolts.
What if you barely have any data to work with? It's a huge problem, right? Well, here's a really clever solution. It's called bootstrapping. With this technique, you take your small sample and use it to create thousands of new simulated samples. It's like making a giant crowd out of just a few people to see how they behave as a group. It lets you build a reliable picture of what's going on without that risky normality assumption.
And now for the final boss of messy data, those wild, unpredictable signals you find in fields like geophysics or in biomedical signals. For this, you need something that sounds like it's straight out of science fiction, the Hilbert-Hong transform, or HHT. This amazing method can take a signal that looks like a tangled mess and cleverly break it down into simpler, understandable pieces. It's a true frontier tool. Now you might be thinking, this all sounds really complicated and slow. And you're not wrong. These advanced methods can be real resource hogs. But here's the cool part.
That barrier is coming down and fast. With better hardware and smarter algorithms, we're seeing potential processing time reductions of up to 90%. That is a complete game changer, making these tools accessible to way more people.
Okay, we've filled our toolbox with everything from a simple hammer to a high-tech laser. Now for the most important part, knowing which tool to use and when. This is what separates the amateur from the master craftsman.
So let's break it down into a super simple 4-step mental checklist. 1. Use your eyes first. Always start with that QQ plot. 2. Ask yourself how much data do you actually have? If it's not a lot, lean towards something robust like bootstrapping. 3. Is your data playing nice, or is it full of wildcards and outliers? If so, prioritize an L moment test. And finally, number 4. Don't work in a vacuum. Know the standards and best practices in your specific field. Context is everything.
And if you remember just one thing from all of this, let it be this right here. No single method is universally optimal. Context and data characteristics dictate suitability. In other words, there's no silver bullet. Being a great analyst isn't about memorizing one test. It's about understanding your data and thoughtfully choosing the right tool for that specific job.
And that leaves us with a final question to chew on. As our data gets more complex and our AI models get smarter, we have to ask, what comes after normality? The future is pointing towards things like Bayesian methods and neural networks that might not need to rely on these old assumptions at all. It's a really exciting frontier, and it's where the whole field is headed next.